Hi all, thanks very much for joining. My name's Chris Given, and we also have Joanne Peacock here with us today, where we're going to be exploring the use of risk tolerance thresholds to set replacement criteria. Essentially, just a quick introduction from me. As I say, Chris Given, I'm Strategic Bid Manager, and I work within our Insights business here at EA Technology, where we support businesses and with strategic decision making through a range of consultancy and software solutions. We also have Joanne Peacock, who heads up our asset investment management team. Joanne's got a wealth of experience supporting organisations around the world, predominantly with asset health and risk-based methodologies to support investment decision making. So in this webinar, we'll be examining the process of setting risk tolerance thresholds for network assets and using worked examples of how this has been applied and refined to support investment decision making. So looking at the agenda items, we'll be covering risk tolerances, asset modelling and risk matrices. We'll be looking at mechanisms for identifying candidate assets for refurbishment and replacement. We'll be looking at concepts of in-year risk, long-term risk, and how this can be used to support investment justification. We'll also be looking at replacement strategies in relation to risk tolerances. And finally, we'll be drawing some conclusions and key takeaways from the session. So all going well, we expect about 45 minutes for the presentation, and that should leave us plenty of time for questions and answers at the end. I suppose as we go through the session, if you do have any questions and you want to pop them in the chat, we can try and find appropriate breaks during the session to try and pick those up as we go. Trusting that all sounds okay, I'll pass you across to Joanne. Thanks very much.
Okay, and just housekeeping as well, we are recording this session, aren't we, Chris?
Yes. Thank you, Joanne. Yes. Just so you're aware, we are recording this session.
Brilliant. It's just so that everybody's aware. It usually flashes up at the top, but in case anybody doesn't know, and it's just really so that we can put the session on our YouTube channel, so that colleagues and other people can catch up with that session later on if they've missed this session. I was going to say this afternoon session, but that will depend on exactly where in the world you are. So, okay, so risk tolerance, asset modelling and risk matrices. So a few definitions just to start with. So we're mainly looking at risk tolerance. So how much risk are we likely to tolerate on our network or within our potentially industrial or power production environments? And so that's what risk tolerance is really all about. So what we want to do is understand the current level of risk, so know what risk we have on our network assets or our infrastructure, understand the level of risk without investments, and then understand what might be a tolerable level of risk. And we can do this by stakeholder engagements, by other activities. We can start to think about the balance between affordability and reliability. So what we've found is that in countries where there is a hugely reliable network, then they would normally place affordability above reliability in terms of a stakeholder requirement. But as soon as the network is not quite so reliable, then the tables turn a little bit and reliability becomes more important. So you have to judge this against sort of your network and what your stakeholders require. And obviously there's a trade-off between the two. We're also going to be talking about just communication of the outputs that we'll show you, and hopefully we'll provide some ways of demonstrating the different risks and the different types of strategy that you can apply to your investment process, and ultimately looking at defining what would mean by a tolerable level of risk and what that means for an organisation. The examples in here have come from a GB, a network operator based in Great Britain, based on some of the work that they've been doing on setting these tolerance thresholds, and they've done that for their regulatory submissions and business planning at the back end of this year and early back end of last year and early for this year. So these are real world examples. Okay, so as with all our webinars, we're starting with common network asset indices methodology, or common methodology for short. We do that because it's a public methodology, and so anybody can pick that up and have a look at the shape of that methodology, and it's something that we've helped to develop as well with the network operators in Great Britain. Other network operators and other customers have started to pick that up in far-flung locations, so out in the States and Canada, all the way through to Japan and sort of New Zealand, Australia. There's a lot of people, organisations who are using common methodology as a sort of basis for their investment planning. So it's a really good place to start, and it has lots of mechanics in there that are really useful and applicable to any network or even industrial electrical assets. So that's our starting point. We're not going to deep dive into the methodology, but there's just a few critical things just to draw out of it. So the methodology assesses the condition of the asset in what's known as a health score, and that's on a scale of 0 to 10. And putting a health score in place is a really useful thing to do, and you can immediately see each asset gets a health score, and you can immediately see where approximately in its lifespan that asset is, whether that's at the beginning of its life, in the middle of its life, and it needs sort of a bit more maintenance and refurbishment maybe, or if it's at the end of its life and it's becoming a bit of a burden on the network, and you're not willing to risk that asset continuing on the network due to the increased likelihood of failure. So that's the scaling we use. So the health score part of the common methodology, and so this is just the left hand side of that little diagram I showed before, so we can just see what goes in and makes up the health score. So we've got age, the location of where the asset is, the duty, which is the workload, health score modifiers, which are your observed conditions and your measured conditions. So observed would be your data collected at inspection, and measured would be things like your PD tests and oil tests, those sorts of things. And then we've got a bit of the bucket for a reliability modifier, and this is just a catch-all to collate any other information that you haven't already captured. And then we can take our health scores, and down at the bottom here we've got our health scores from 0.5 to 10. You might be wondering why 0.5, and it's because we use the health score as a multiplier, so we can't start at 0. And then on here I've also plotted the probability of failure curve, and the way this is calibrated in all of the asset models for every asset, it's calibrated such that an asset at a HI of 10 is 10 times more likely to fail as an asset which is on this flat part of the curve. So that's up until a health score of 4. Within the methodology, we also have this magic number of 5.5, and this is defining the maximum allowable health score that an asset can have without specific data that tells us it's in poor condition. So this is the maximum it can have based on its age, the duty, and the location. We stop it at 5.5 for the assets in common methodology at the minute. That said, these rules might slightly change into the future as we start to look at different asset types, but currently 5.5 is we're saying we won't condemn an asset until we know that there's something actually wrong with that particular asset. So if you don't know there's something wrong, you need to go and collect the data. That's the basis of how the methodology works. And then the other important thing on this slide is that we also have these HI1 to HI5 buckets, and that's to allow us to do some matrices and some very easy matrices using the scaling of HI1 to HI5. And so by the time you've put all your assets through the methodology, you can start to produce histograms like this. And I know this isn't HI1 to HI5, this goes up to 10, but these are equal buckets of 0 to 1, 1 to 2, 2 to 3, etc. In this particular diagram. But what this shows is the progression for an asset population from the current point in time, so that's year 0, up until year 8. And we can quite clearly see, very easy, that the darker blue colour is the year 0, and there's more assets over on the left-hand side of the chart, and then the lighter blue is the year 8, and we can see that those assets have transitioned. So, for example, for HI9 and HI10, there were no assets in there in year 0, and there now are in year 8, sorry. So there's a general movement towards the right-hand side, and that's what we would expect. Okay, so now we want to move on and very briefly look at the average, the consequences part of the model. So within the consequences part, we're looking at essentially 4 consequence categories. So financial consequences. So these are the consequences of failure. What do we expect to happen if an individual asset fails? And so the most obvious one is there is some financial cost to that. So if it's something like a switchgear that's failed to trip, there might not be a lot of cost to that. Or there might be some other incipient or sort of degraded failures where you might need to go and see that asset and do something, and there's a cost for sending somebody out, and the operational cost, and maybe some parts. There's also a catastrophic type failure, and that would require a complete, you'd lose the asset, and so you'd have to put in a new asset. And that's in monetary terms already, that's an actual dollar value already. The safety consequences is the possibility of injuring somebody in the event of that asset failure. Fortunately, this doesn't happen very much, and so you find that the safety consequence values tend to be really low. They don't tend to dominate the consequence sums. And again, we turn those into monetary value, and rather than think of it as cost of an injury, we think of it more as a cost to prevent the loss or the possibility of an injury. So that's what we're really trying to capture in safety. And then for environment, we're trying to capture things like loss of SF6 into the environment, which is very potent. We're trying to capture loss of oil into the environment, especially if that asset is located near a watercourse. And then also things like waste and disturbance. And we've put monetary values on those in the methodology. And then network performance or security supply or asset performance, it's sometimes termed, that's the purpose for the asset actually being there. So that might be sort of SAIDI numbers in a network environment. It might be the loss of production in a solar plant. It might be, again, loss of output for a manufacturing organisation. So you do have to take that one and apply the correct methodology in that instance, depending on where you're applying the actual overall sort of methodology. And so taking these consequence values, we can then put them into category. We can then create an average consequence, and that's what we've got in this table here for various different asset types. Tends to be dominated by network performance for most. This is a slight, and then financial. It's a slight exception that we've got some which are slightly higher for the financial, but generally network performance often dominates most of the asset classes. And then once we've got the average consequences of failure, which are designed for the average asset, we can then look at specific assets and we can define what we call a criticality factor. And so an example of a criticality factor for, say, safety might be that if an asset is located in a populated area, then that asset has a higher safety criticality factor. And we multiply the criticality factor by the average consequences to make the consequences of failure in each one of the consequence categories, and then we can sum those up, which is in dollar value. So other examples might be the numbers of customers associated with a particular asset, and we'd put a factor in there for network performance for that one. For something like a financial, it might be things like the size of the asset or the construction of the asset might drive the financial one. And then once we've got our consequences of failure value, we can start putting them into this sort of lookup table at the bottom. And what this is telling us is that for assets that are up to 75% of the average, we're going to classify those as a bucket, C1 bucket. For assets that are an average consequence, so that's from 75 to 125% of the average, we're going to call them C2. And then for assets which are 125% to twice as 200%, that's a C3. And then above that, it's a C4. And that's how we're starting to bucket the assets. And so once we've created our little buckets, so we've got the HI1 to HI5 for probability of failure, which relates to the health score, and then we've got the consequence of failure. So we've got this really nice, easy matrix, and we can produce these matrices for a particular asset fleet, and we can also do it for, say, a substation or a particular manufacturing plant or a circuit or an area, or, you know, because you've got the right because you've got every asset represented. And at the next slide, this shows a typical population of about 30,000 assets, and they're represented in these buckets. And now we're at this sort of slightly higher, more abstract level. We can start looking at things like risk tolerance and start having these conversations with our stakeholders about, are we happy with these assets sat over in this HI5? And you don't need to know what asset type it is, but you know that this is, you know, the assets in HI5 are, you know, more likely to fail, and there is higher risk associated with them. So that's what the risk matrix does. And generally these are used by sort of asset managers, planners, and also management. And so once we've got to that stage, we can now start thinking about our replacement and refurbishment processes and identifying different candidates of asset that we want to replace or refurbish. And so the impact of the replacements and refurbishments is really to take an asset from one bucket and move it to another. So for a refurbishment, you're basically saying, we're going to take this HI4 asset and we're going to do some refurbishment, improve the condition, and then it's going to be a HI2 asset. And you'll process that through the formulas to make sure that, you know, you're recalculating the asset with its new data based on its new condition, and it will end up with a new health in HI value. For a replacement, we do go through the same process of resetting all the things like the age to 0 and all the condition points to be as new. What that will do is they will always go into a HI1 bucket. And if you're doing a like-for-like replacement, it nearly always goes to the same criticality bucket as its predecessor. And that's because it's the criticality is more based on the location and the number of customers or the duty of the service it's producing, rather than changing asset category. There are one or two exceptions, but normally you would go from one HI5 to HI1 in the same category. Non-like-for-like replacements, you would see a drift potentially up. So if you went from an oil-filled asset to an SF6 asset, then you might see that criticality reducing. But like I say, the criticality often is, you know, based on the financial and the network performance, the two biggest drivers. So you may not see that big improvement with the replacement. So looking at candidates then for replacements and refurbishments. So on the table that I've got on screen, we've got 4 assets represented, and I'll just go through very quickly the different columns that we've got. So we've got the current health score. So this comes out of the methodology; it drops out, and then you've got a couple of ratios, and these things are not in the methodology, but they're things that we add to our models because they help us understand a bit more information about what's going on with the asset. And so the age over expected life ratio tells us how far through the lifespan that particular asset is. So basically, is the asset at end of life? So for the first asset, that's 0.23. So that's only almost a quarter of the way through its life. But then for the third asset down, that's more than 20, that's nearly 25% over the asset life. And so we can sort of judge roughly where the asset is. And then the B2 B1 ratio, again, this is these terms are used within the methodology themselves. So B1 is what is an aging rate that we set right at the start. So knowing nothing other than the asset type and where it's located, we can define an aging rate based on how long we expect that asset to be in good condition on the network. So that's what B1 is. But then after we've calculated our health scores, we then recalculate an aging rate based on how quickly that asset is actually aging, and that's what we call B2. And so if you look at the second asset down, that's a value of 2. So that tells us that it's aging at twice the rate that we would expect, which is unusual, a little bit unusual, but can happen. But for the other assets, so the first asset's aging a little bit slower, and the third one as well, and then the bottom asset is aging approximately where we would expect it to be. The third column is what we call condition flags, and what these are when we've processed our methodology, we go back and we have a look and see what are the key drivers that are making the health score what it is. So we can quickly say that second asset, external condition, is the one that it's just one thing in that flags, and that is telling us that there's external condition problems. But then the bottom asset, there's reliability, duty, and external condition. So there's a whole range of things going on with that asset. And so just by using these 4 data points, we can then put some automated guide for investment. So for the first asset, it's got a low health score, it's new, it's not aging quickly, so we don't expect to do anything with that over the next 5 to 10 year period, other than any regular maintenance and also refreshing of those observed and measured condition values at regular intervals. So that one's going to give us no problem in all likelihood. But the second asset, that's a health score of 8. So that's really saying that asset is at the point of failing in some way, but it's only 0.38% of the way through its life. So it's quite a young asset to be in such a poor condition. And we can see it's aging at twice the rate, but it's only got one issue wrong with it. So if we have a refurbishment that will deal with that single issue, that external condition, then that condition of that asset will come back down to a very normal level, which for an asset at that point might be, say, I don't know, a health score of, say, 2 or 3, and then you can expect a normal trajectory in all likelihood for that particular asset. For the third asset, so if you remember, we had this magic 5.5. So this is an old asset, we know that. It's over its expected life, it's old, but it's aging slowly, and it's not got any specific condition information, and there's no condition flag, so it's old but good condition. So we don't expect to do anything with that immediately, but we continue to monitor that, and potentially that's a replacement candidate in the future, probably because the overall degradation, when it does require it, it probably wouldn't be worth repairing at that point. So that would be a replacement. And then the bottom one has got a moderate health score, 6.7, but we know it's aging about approximately right. It's 80% of the way through its life. It's got a range of things wrong with it, so that becomes a replacement candidate. So this doesn't take away engineering judgment by having these automated things, but it just allows us to look and set, these flags and these ratios against the assets so that we can easily and quickly see what's going on with them. And then we can look and move those forwards into an investment type program. So now we'll move on and look at the in-year risk, long-term risk, and investment justification. Lots of things going on in here. So in-year risk is what most people just call risk. So this is COF times POF, or probability of failure times consequence of failure. It's done slightly differently in common methodology, and it's actually that the assets have been put into buckets. And so the in-year risk is a typical POF within a health index band, so that's a HI5 band, and that typical POF is represented by the table on the left-hand side. So for HI1, we've got a typical POF based on a health score of 1.23, and you can see those for the other health index bands. And then it's multiplied by a typical COF for the, it's not actually, yeah, it's multiplied by a typical COF, which I'll show on the next screen. But the POFs are on screen for certain selection of asset types, and we're using the regular common methodology version of how we convert health score to probability of failure, which is using this cubic equation, which I've also put on the screen. So for the COF side of things, what we want to do is we look at the typical in-year risk, and we want to multiply that by a sort of average for the band. And so the C1 to C3, we've got the average consequences in each of those bands, and then that's just moderated by a multiplier in methodology. And what this does is it just gives us an average for every asset. So once you get to the 5x4 matrices, you've got it is basically averages. And the reason they've done that is just a simplification. You could quite easily do POF times COF, and you could work that out for in-year risk. But then the next stage is we're going to look at the long-term risk in a second, and that requires a lot more formulation. And so really, whether you do that on an asset-by-asset basis or in a sort of averages basis like common methodology, that's kind of up to yourselves. But there's a lot more formula if you do it asset by asset. And then, so just to complete the in-year risk, so we've got our HI1 to HI5 probabilities of failure, and we multiply those by those averages, and then that gives us, for each asset class, we've got this nice 5x4 matrices. For every, we've got the values for every one of those 20 squares. And so the actual replacement cost, so in this example, so I've converted it from GBP into US dollars just for reference and convenience sake. We're looking at 33 kV transformers in this case, and the replacement cost for that is 480,000. So going to somebody and say, right, we've got this HI5 asset, and even if it's at C4, it's quite hard to justify until you start looking at more parameters. It's difficult to justify spending 480,000 to remove potentially what would be £40,000 worth of risk, $40,000, should I say, worth of risk, and that would be the HI5 minus the residual risk to give us the approximately 40,000. So that's quite a hard sell, and sometimes stakeholders get a little bit hung up on why we need to do that. So this is, if you're familiar with common methodology, this is one of the differences between Common 1 and Common 2, in that for Common 1 we just looked at in-year risk, we just had this concept of that, but for Common 2 we're more getting closer to what is a more traditional CBA type approach, but it's a simplified CBA, and within Common 2 we're now looking at the benefit that you get not just in the current year for the replacement, but in the future years that are to come. And it looks at 30 future years, and that's because we have a government green book, and that tells us that that's what we should be using for the discounting, the time period for the discounting for the calculation of long-term risk. So we do have some references back to sort of some government sources for that. And so long-term risk, I'll start very quickly with the formula. I'm not going to go through it all, but the COF is static. There's an assumption that the consequences of failure is static, but the discounting and the summation is done on the POF side of things. So it's looking at the summing the POFs times the consequences for every year. And there's a discount in there. There's a discount in there, discount rate. And what we're using long-term risk for then is we are starting to define our asset population in terms of long-term risk. And by doing that, we're then setting targets and monitoring progress against those long-term risks. And we're also using it as a way of justifying asset investments. And we'll go through those in a second. So the current year long-term risk then for any asset profile. So this is our profile that we had before with all our almost 30,000, I think it's 30,002 assets. If we multiply that by the long-term risk, so literally HI1C1 times HI1 times C1, and for all the categories, we get a value, again in dollars, for our asset population, which is $7,116 million of long-term risk on these assets on the network. So once we've got that figure, we can start to look at what the long-term risk benefit is. And I know CBAs will do this, but this is it's a really simple way of doing this for any asset. And we do this for every asset class, and it's quite straightforward. So simply, long-term risk benefit, or LTRB, is the long-term risk. So that's the value, say you were in HI5C4. So that's the value in this blue circle, minus the residual risk. So we know it goes to a HI1. So that's this value here, plus the cost of replacement, which is 480,000. So we're taking it from HI5 all the way to HI1, quite simply, and the numbers are there for that particular one. So for HI5 C4 asset, the benefit of doing the replacement is over $2 million US. So that's how much you'll save doing that particular replacement. And then what we can do is look at every square in the matrix, and if we assume like-for-like replacement, we can basically take every HI5 or 4, 3, 2 asset, and we can assume that they go back to HI1. And so for every square, so that 1.6 here is the same as the 1.6 here, and we can see which assets would be justified financially under this process. So for a HI1 asset, clearly you're spending money, you're not reducing the risk, so it's only going to cost you so the 480,000, which is the value of the actual investment. So you don't gain anything by doing that. It's only when you come to the HI4s and 5s and this one HI3 that you're actually starting to reduce the risk. And what you notice in this particular example is, the figures work out slightly differently for the different asset types. You don't always get exactly this pattern, you get slightly different shapes to it. The HI4 asset at C4 is higher, you'd take more risk out than, say, a HI5 asset at a C3. And that just shows the importance of these HI4 assets, because strategically they're highly important. So we'll move on and look at replacement strategies and risk tolerance. So what we've got in this next section is 3 examples of just different strategies that you could take or you could use using our long-term risk and our cost-benefit approach. So within this first one, so with each of these strategies, I've put a year 0, which we've been looking at all the time. And then I've also put the profile for year 5. So this is moving those assets 5 years into the future, and you see there's more, say, HI5 assets and fewer HI1 assets. And then within this strategy, we're looking at replacing the justified investments. So all those green squares that we saw before, if you took all of those assets in those green squares and you replaced all of those assets, you'd be left with a really low, you'd be left with quite a low health score profile and much lower overall long-term risk. So it will reduce the risk significantly. That's just going to happen. And you can justify those replacements because you've got this CBA that tells you that you can do so. But the problem with it is that you don't maximise the lifespan. So particularly that HI3 one where it's green, even though it's a critical asset, you might, if it's truly that critical, you might replace it at a HI3. It depends on your attitude to the risk of those assets. In GB, we probably wouldn't replace those. We would maximise the lifespan and replace them much later. But this CBA gives us those options, and it helps start that conversation in terms of which assets we're comfortable leaving and which assets we really feel like we need to remove off the network. So that's the first strategy. Another option that could be taken, and some of the network operators in GB have done this, is they've taken actually their worst health score assets. They've basically said, we're just going to replace those worst health scores. And so you can see that the HI4s are untouched, but all the HI5s have gone in this future with intervention profile. And again, that significantly reduces the risk and we can justify it, but it does ignore these higher criticality assets with lower health. And whether that's the right thing to do, again, that's a bit subjective and due to judgment. But it does improve the lifespan, so you're getting sort of the maximum life that you're willing to risk for those assets. And again, it's moderately expensive, but it does improve reliability. But another approach, and again, this is based on a UK example, what the company's decided to do is set what we call these risk tolerance points, which I know is kind of, it's late in the webinar to sort of to finally sort of put some precise definitions on these. But these risk tolerance points they're basically saying that for the asset class, and they are different for different asset classes, but we're saying that for a C4 asset, we're actually going to replace this. We're going to be much more sensitive. We're not going to use the HI4, HI5 buckets as such. We're going to be much more sensitive than that. And we're going to say, right, for a HI4, we're going to replace that at 7.75. So that's the defining points that the engineers and the stakeholders have come to and said, this asset's going to be 7.75. And then for a C1 asset, we're saying that we're going to leave that to a HI10. So that's really quite late. So there is a significant risk of asset failure for that asset. But they're willing to take that risk for the particular asset population this is for. And so the impact of this is that it reduces the highest risk, and you're now able to reflect that criticality as well as the consequences. But we're not saying we're going to do every HI4 or every HI3. We're saying we're only going to do it once it gets to a certain point. We know we can justify it. We know we can talk about it with our stakeholders and agree it. I dropped out for a second. I'm so sorry. Hopefully that won't happen again. But we're balancing asset lifespan and risk in this approach, and it moderates expenditure. And so, again, these are real examples. So the question is, what thresholds do you actually set? So I think, I can't remember which asset group that was now, but I put some examples of some of the asset groups, and it would be nice to think you could set the same for everyone, but reality is a little bit different, and some engineering judgment has gone into setting these threshold points. So for 11 kV switchgear, so we class that as a HV switchgear in the UK, the C1 point is 10. That's really quite late, and C4 is 8.5. And again, that's getting towards a really sort of quite a long lifespan for the asset, a really quite a poor condition. But I guess the reason that they've done that, and I've put some engineering justification there, is there's no moving parts. And so they are willing to let those go slightly longer. Experience shows that some of those assets last longer. But also there might be things like logistical reasons, the availability of spare parts, the availability to get crew in to change those particular assets. Whereas for the 33 kV transformer, they're much more conservative. They're much bigger assets. And so they're not willing to let them get into such poor condition. And there's more, there's more moving parts. They're more mechanically, there's more likely to go wrong with the discrete parts of them. So they've set those lower. And then the poles. Poles are an interesting one in the UK because we'll have a lot of underground network, but a lot of our sort of towns and cities are primarily fed with poles. So we've got a lot of pole overhead lines. And so those poles tend to be close to people. And so for that reason, they've said that there's a high safety consequence of failure to employees, but also to the public, just because of where those tend to be located. And you can't really reflect that in your criticality, because safety does tend to come quite low. It's quite a small criticality value. So you don't see high safety criticality driving the consequences for an asset class. Conductors is for a different reason. So they've decided on 8 again for conductors, and to some extent fittings is quite similar. And the reason for this is, especially for conductors, is there's so few condition points that they collect, that they find that the health goes from really okay and quite good to quite poor quite quickly. And that's because the inspection cycles are quite long and there's not a lot of different data points. So for a transformer, you're collecting lots of data points, you're collecting them manually, for example. But for a conductor, as soon as you see degradation, then you need to do something about that quite quickly. And it's quite similar for fittings. They tend to accelerate through the health scores quite quickly. And so there's quite a conservative replacement point put on those. And so just to complete the lineup of our little profiles, I've put on there the strategy 3, and I've implemented that in our example. And you can see how all the HI5 C4 assets, they've all gone. They're now HI1 assets. But we've also lost some of the HI5 sort of C3s and some of the C2s and C1s as well. But critically, we've now lost some of the the C4 HI4 assets as well. And so just to put a bit of a summary up so that we can compare the different strategies. So as we saw, a very high long-term risk. This is for 5 years, so this has obviously gone up from the 7,000 million that it was previously. So this is now year 5. And then we've got the justified replacements. So this is really moving it down to a very low point, but we can see the number of investments is actually huge, and the investment cost is huge as well. And then if you take one of the more sort of strategic approaches, you can see you get much better risk reduction per investment. And again, these are in millions. So it's it's sort of similar to the HI5, but it's a more subtle approach. And yes, there is more risk here on this approach, but we're also doing a lot less investments, and that's why the risk reduction per investment is actually greater on this one, and that's really a key metric. But it's quite easy to go back to our models and set those replacement points slightly differently, or to do some optioneering and talk to stakeholders and say, well, if we take a more affordable approach and move some of those replacement points upwards, so we're taking more risk, you can see what the impact of that is. And so it's quite useful, and I've calculated those numbers just for this sort of session, and it's quite easy to do that and quite quick and straightforward to do that. So in conclusion then, so just a few things just to wrap up. All of that is based on the asset health and the risk methodology, and that's really the foundation of what we're doing. If that methodology is not right, if it's not calibrated, if it's not telling you the right assets are in the right condition, nothing else really holds up once you start coming to these sort of matrices levels and start doing this optioneering. It's your absolute foundation level. You need to get your asset health and criticality right, which is arguably the harder part of this. And then obviously there's the regular assessments, your data, and the importance of that data being up to date and really reflecting the condition of the assets. But we have learned that long-term risk can be used for the setting and evaluating of risk targets and the basis of the justification of investment. We've also looked at the flexibility of setting those intervention points and capturing those nuances and why that is an engineering judgment as well as a sort of stakeholder engagement type exercise. And then hopefully what we've also demonstrated is that those matrices, they're really clear and they're really easily communicated to different types of stakeholder, whether that be engineers, people on the ground, or whether that might be your sort of CEOs, CFOs, presidents, or regulatory bodies. So hopefully they will be of some use. So the things that we haven't really talked about, and when you're building an asset plan, a couple of things that we didn't really have time to fit into this session is one is phasing. So that really is the deliverability aspect of this. So you can't really propose something which you can't deliver. What we found is that there tends to be a bit of a backlog sometimes when you first implement this, and quite a lot to do in the first year or couple of years, and then it sort of smooths out. But you really want to make sure that your deliverability is there, and you're working within the constraints, and that might mean that you have to drift a little bit from those ideal investment points. And again, while we're talking about drifting a little bit, you'll also want to consider the other reasons why you want to invest in particular assets. So not just condition based, but things like load related investment, policies that you're implementing, net zero, even things like, I know I dropped out again, that keeps happening, but net zero targets, things like that. You'll want to combine those so that you're only visiting, say, one substation once to do all the works that are required at a particular time. So you'll want to group those together into an optimized plan. So that's the end of, everyone's very quiet and I don't see any hands up yet. But that's the end of the presentation. I hope that's really made, I hope that's made some sense and you found that useful.
Some really good information in there and a lot to take in. I appreciate that. But obviously, if there is any questions that anybody would like to raise, please feel free to either unmute yourself or pop it in the chat. Or
So while you're having a think about that, I'll just put it onto the next slide just to say, and I'll just say a quick thank you from me and Chris as well for attending and listening to the webinar. We're doing monthly webinars at the minute, and so the next one's on defining failures, failure rates and probabilities of failure. So that's the next one. That's going to be in March. Thanks, Julie.
also, just to let you know, we will be sharing the presentation slides, and if you wish for a copy of the recording, please do get in touch and let me know. I'm sure we can share that with you also. Obviously, contact details at the start of this presentation. So if you do have any questions beyond this session, please feel free to reach out to either myself or Joanne. We'll be happy to help. Thank you.
Well, it is very quiet, so maybe we should end the session there. But again, just to thank you for turning up and listening to the presentation. Feel free to connect with us on LinkedIn and obviously follow us. We do put out posts and things every now and again, and it's always interesting to see who's attending and just see what we're always interested in what other network operators are doing and industrial customers as well. And yeah, just happy to hear from you and share your experience. Thank you very much.
Yes, thanks all. Take care now.
Thanks. Bye now.
Bye now.